So in this video, we're going to do some more exercises to practice on how to define a transition probability matrix. So there are two things you should be able to do. First is defining all the possible states, and then second, define the probability of transitioning from one state to the other state. So let's take a look at the first problem. So in this problem, a company has two machines. And then during any day, each machine that is working at the beginning of the day, so you see there's a blue dot here next to machine 1, it means that at the beginning of day 3, you inspect the machine and you find that the machine is working fine. So if a machine is working at the beginning of the day, it says that it has a chance of 1/3 of breaking down during the day. Okay, so you really need to pay attention here, which is that you inspect the condition of the machine at the beginning of the day, but then the machine may breaks down during the day. So if a machine breaks down during the day, let's say it breaks down during day 3, which means that at the beginning of day 3, it is working fine, and then it keeps working until one point during day 3, it broke down. Okay. And then if a machine breaks down, it will be sent to be repaired, and then it will be working again 2 days since it breaks down. So if it breaks down during day 3, it means that the machine will be fine again at the beginning of day 5. So this means that at the beginning of day 4, the status of the machine is broken down. So for machine 1, in this case, at the beginning of day 3, it is okay. At the beginning of day 4, it is broken down. At the beginning of day 5, it is okay again. So why do I emphasize the status of the machine at the beginning of the day? Well, it's because here, if you read the problem carefully, you see that here it says the state of the system be the number of machines working at the beginning of the day. Okay, so that's why I really emphasize that machine 1 at the beginning of day 3 is okay. At the beginning of day 4 is broken down. At the beginning of day 5 is okay. Suppose the case for the second machine is that it is working fine all the way from day 3, day 4, and day 5. It means that for all of these days, the status of the machine 2 at the beginning of each day is fine. The problem specifically wants us to define the state of the system to be the number of machines working at the beginning of the day. But I think it's kind of a little bit more difficult to jump directly into the number of machine. So I will usually try to write down the story about the condition of each machine. So let's say at the beginning of day 3, the condition of machine 1 is working, and the condition of machine 2 is also working. So the first W means machine 1 is working at the beginning of day 3, and the second W means that the second machine is working. So what are the possibilities for these two machines at the beginning of day 4? Well, you may have both machines working. So we have WW, and then you might have the first machine working, the second is broken down, and then the third one is what is shown here. The first machine is broken down, the second one is working, and then also is it possible that at the beginning of day 4, the status of both machines is broken down. Okay, but from day 4 to day 5, we cannot know for sure what happens, because if a machine is working in day 4, then in day 5 actually you also have 4 possibilities like before, right? So the possibilities is WW, working, 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 broken down, working, broken down. But we don't really need to care about what happens in day 5, because if you remember about Markov chains, we try to model what happened in a particular time based on the information from one time step before what we are interested at. So here we only need to care about, let's say, day 3 and day 4, or in other words, day t and day t plus 1. In the previous slide, we've seen all the possibilities if we start day 3 with both machines are working. But it is possible that in a particular day, we start that day with a machine that either one of them is broken down, either machine 1 or machine 2, or we can also start the day with the status that both machine is in the status of broken down, right? So let's take a look at how that could happen. So if in day 3 we start the day seeing that both machines are broken down, it means that both machines must have been broken down during day 2, right? Because at the beginning of the day, you can't just have suddenly the machine is broken down. It just can't happen. So the only possibility is that you start day 3 with both machines broken down means that they broke down during day 2. What does this mean? This means that 2 days later, since it's broken down, so day 2, day 3, day 4, it will go back to be a good condition machine, right? So it means that if on a particular day you see that both machines are in the status of broken down, it means that in the next day, that machine will be working. So if both machines are broken down at day 3, at the beginning of day 4, they will both working. So what is the probability that a machine that is broken down today will be working tomorrow? The probability is 1. Okay, because if a machine is broken down at the beginning of this day, it means that it broke down during the day before, such that the next day it will be already fine. What I'm trying to say here is that don't be confused with the problem that says it takes 2 days to repair a machine. 2 days is from here, since it breaks down during day 2, and then 1 day up to day 3, and then 2 days up to day 4. So whenever a machine is broken down, you can say that in the beginning of next day, it will be fine for sure. So that's why the probability from B to W is 1, and then you multiply this because you want to say the probability of B to become W and W. So here's the other probability computation for the other possibilities. From working to working again is 2/3, because the probability of breaking down is 1/3. So probability from working to working again at the beginning of the next day is 2/3. So the probability of both machines working at day 3 and they're also working fine at day 4 is 2/3 times 2/3. Another extreme is that here, if you see today at the beginning of day 3, both machines are working, the probability that machine 1 will break down during day 3 is 1/3. So this is the first 1/3. The probability of the second machine will break down during day 3 is also 1/3. So here the probability for having both machines breaking down in day 4 and the beginning of day 4 is 1/3 times 1/3. So using the same idea, you will have these probabilities. So again, let me give you an example here. Why this is 1? Because remember, whenever you see the machine is in the status of breaking down at the beginning of a particular day, on the next day, it must be in the status of working fine. Okay, now that we've got all the complete story about the condition of each machine at the beginning of day 3 and day 4, now we can start drawing the transition probability like the problem wants, in which the states are 0, 1, 2, means that the number of machines that are working at the beginning of the day. So let's start with 0. 0 means no machine is working at the beginning of the day. Or in other words, both machines are broken down. From the previous slide, we know the story that if a machine is broken down at the beginning of day 3, at the beginning of day 4, the status must be working. So that's why the probability from 0 to 2 is 1. Because if you have no machines working at day 3, at the beginning of day 4, you must have both machines working fine. So you have 2 machines working. That's why we have an error from 0 to 2 with the probability 1. And then if you have 2 machines working at the beginning of day 3, at the beginning of day 4, you will have 2 machines working with probability 4/9. And then you may also have no machine working at the beginning of day 4, which means both machines breaks down during day 3 with the probability of 1/9. And then you may go from both working, so 2 machines are working, to only 1 machine is working at the beginning of day 4. But then there are 2 possibilities here. Maybe the second machine is breaking down. Maybe the first machine is breaking down. Because there are 2 possibilities, so we need to add these probabilities, these 2 probabilities to become 4/9, from 2 machines working to 1 machine working. However, when we consider the state of 1 machine working, we don't really care whether it is WB or BW, because the probability of machine 1 and machine 2 to experience breaking down is the same. So we can just think about both of these are the same state. Okay, we don't need to differentiate whether 1 machine breaking down is the first or the second machine. Because we consider them the same thing, we can just put the probability from 1 to 2 equals 2/3, and then probability from 1 machine working to 1 machine working as 1/3. So this would be more complicated if you have a different rate of breaking down for machine 1 and machine 2. Then you cannot do this. Here, because you have the same possibility of breaking down for both machines, then you can do this. Which what I meant is you can just ignore whether it is WB or BW. You can just put this probability from 1 to 2 equals 2/3, and then from 1 to 1 equals 1/3. You may also ask, can we use the states WW, WB, BW, and BB? Well, yes, we can actually. It's just that this problem specifically wants us to define the states as the number of machines working at the beginning of the day. In the real world, how do you decide what is the definition of your state? It really depends on your purpose of analyzing this problem. So maybe 0, 1, 2 is more suitable. Maybe WW, WB, BW, and BB is more suitable to your purpose of modeling this problem. So we do this 0, 1, 2 just because the problem specifically wants us to define the states like that. Okay. So from this exercise, what I like you to really think about is that when you have a problem that says during a day something happens, and then what happens on the next day, and then you inspect the condition of the machine at the beginning of the day, you may want to draw a timeline such that you have a clear vision about what happens at the beginning of the day, during that day, and the beginning of the next day. Because usually students are quite confused with the wording in the problem that says it takes 2 days to repair a machine. Okay, so don't be confused with that. Draw the timeline and realize that you inspect the machine at the beginning of the day, but the machine may be broken down during that day. Also in this problem, you need to pay attention to what the problem wants. In defining the states, it wants us to define the state as the number of machines working on a particular at the beginning of a particular day. I have another problem as an exercise, so see you in the next video.